Thank you for the introduction. So today I'm talking about these weak equivalences between algebraic weak domain categories, and this is based on joint work with Soichiro, who's at Macquarie right now, and Keisuke sitting over there. So let me start the talk by, first specifying exactly what I mean by a weak domain category. Intuitively, this is a sort of higher category-like structure where you have n cells for each n, and you have all the usual identities and competitions, but the unit law, the associativity, the interchange, and everything only hold up to suitable invertible higher cells. So exactly how we encode this is So first of all, our weak domain categories will be globular sets. So these will be perceived over the category of globes. So we just have these cells in each dimension, and they have the usual familiar shape of globes, so that an n+1 cell lives between a parallel pair of n cells. Okay, so we start with this category of these globular sets, and then we encode all the identity and composition and all the structure using a monad, which I'm calling T weak. And our weak domain categories will be the algebras for this monad. And how do we define this T weak? So one thing we can say is that whatever this notion of weak omega category is, we want the strict omega categories to be a special case of these weak ones. So at the level of monads, there should be a monad map going the other way from T weak to T strict, where the T strict is the monad for strict omega categories on the same category of globular sets. So the way we define this T weak, or rather really this pair, T weak and T strict, T weak and alpha, is that this T weak is the initial Cartesian monad over T strict with construction. That's some words, but what this means is that T weak is the universal monad equipped with this sort of lifting operation. So here, this is the n globe, so this is the representable globular set. So what this is saying is that if we have a commuted square like that, where so at the bottom here is the n globe, and here is the boundary of the n globe, so that's the parallel pair of n-1 cells. So this lifting operation is, so whenever you give this sort of commuted square of this form with this the component of this monad map at the globular set alpha, we always have this chosen lift up here indicated in orange. So this is our definition of T weak, and so this definition is due to Tom Leinster, and also this is based on an earlier idea of Patanin's. So a weak omega category for my talk is an algebra for this monad T weak, which is defined by this sort of universal property. Now, so in what sense an algebra for this monad like a weak omega category? Well, let me show you how to construct at least the identity and binary composition, in this framework. So a weak omega category X is an algebra for this monad T weak. So a weak omega category X is a globular set with this algebra structure map. And let's take an n-1 cell of this little x and try to construct this identity n cell on X. What do? We draw a diagram like this. So what are we doing? So on the left here, this is the commutative square, and what we are doing is, so this X is an n-1 cell, and if you go to the free strict omega category generated by this X, then, by this unit, we have this copy of this little X, and because this T strict of X is, we know it's a strict omega category, so there we do have just the identity n cell on this little X. So that's what this map is picking out. And at the top here, we have to sort of specify what to do on the boundary. The boundary of this n cell is a parallel pair of n-1 cells, and there we just take this copy of little x twice, again using this unit. And so now, because the alpha was a monad map, this square commutes, so we have this commuted square of the form that was on the previous slide. So we have this lift. So we compose that lift with the algebra structure map. And so that specifies an n cell in X, and that's what we call the identity on this little x. And with the binary composition, we do the same sort of thing. So given a composable pair, F and G, we just first look at these copies of f and g in the strict omega category generated by x, and there you can just compose them because it's a strict omega category, and then you lift it up to the weak world where you have to specify where the composite should point from and to, and it should point from x to z. So we just say that, and then there's a lift like this, and then we compose that with the algebra structure map, and that's how we define this composition.
Is the red lift defined as structure?
Yes. So this T weak is the universal thing with those chosen lifts.
Chosen.
Yeah.
Are they coherent in some way?
No. Like this. Just chosen lifts. Okay. So you can see that basically here I'm defining the identity and for the composition by looking at what you do in the free strict omega category, and then you lift it to the free weak omega category, and then use the algebra structure map. And well, this works not just for the identity and binary composition, it basically works for everything. So the slogan here is that a weak omega category in this sense has all the operations that a strict omega category has, because basically, well, given an operation that you want to lift, you just have to specify that exactly what it is in the strict omega category, and then you do this sort of thing to lift it to the weak world, and then you compose that with algebra structure map, and then you get the corresponding thing in this weak omega category. And when I say all the operations, this includes what you usually think of as relations. So let me show you an example. So let's consider the unit law. So, I just showed you how to construct the identity and binary composition. So you can combine these things and talk about the operation that takes, say, a one cell F in your weak omega category and outputs this composite of the identity and F. And although I've been calling this thing the identity, it's not the strict identity because, we haven't enforced any law like that. So this is just some one cell in your weak omega category X. So we don't have that this is equal to F. However, if you go back to the strict world, there is an operation that takes a one cell F like this and gives you back a two cell like this. So this points from the composite of the identity with F to just F. And in the strict world, the top composite is just F. So this is just the identity two cell. But if you think of this as an operation that takes this one cell F and gives you back a two cell pointing from the identity composed with F to just F, then you can lift that operation to the weak world. And then so in the weak omega category, we have this operation that takes F and gives you back this two cell, which I'm calling rho F. And this is sort of giving you a witness to the unit law. And of course, you can get the thing pointing the other way, and you want this rho and what I'm calling rho check here to be somehow inverses to each other, and also you can sort of witness that by an operation that takes an F and gives you back a three cell like this, which points from the composite of rho and rho check to the identity, and so on. So in this way, you can sort of get all these witnesses to the unit law, somehow witnessing the the witnesses and the witnesses to the invertibility of these witnesses and so on, and all these things combine to give you a witness for the fact that this rho and in fact all the higher things as co-inductive equivalences. And I'm not gonna say too much more about this notion of co-inductive equivalence. Partly because my talk at the city last year was about this notion, and also you're going to hear more about this notion in the next talk if you stay in this room. Anyway, so this is somehow the suitable notion of equivalence in this context. So here is the slogan again. So weak omega category in a sense has all the operations that a strict omega category has, including what we usually think of as relations. So for example, unit law is encoded in this way. So unlike other non-algebraic models of higher categories, this sort of allows you to okay, so say you have some statement about strict omega categories that you want to generalize to the weak case. Well, what you do is you look at the proof of the strict case And there you might be using some relations in there which we don't have, but we can just encode all these relations as operations. And once we phrase the proof, like just in terms of operations, we can just lift all these operations to the weak world, and there somehow, like whatever was true there should just like now be proved in the weak world. Because I mean, except that like maybe like you had an equality in the strict world, but you only have an equivalence in the weak world. But somehow like you can just generalize like not just the statement but also the proof from the strict case by encoding all the relations that you're using as operations. So if you actually do that, then the fun part or the tricky part, depending on your viewpoint, is like actually correctly identifying what operations you actually need in a given situation. Because like, you do have all the operations, but like they're encoded by that lifting property. So like you don't have the list of operations that you have access to. So you first have to like sort of identify all the thing that you're using in the strict world, even the thing that somehow implicit and you don't usually think about in there. And then you take all these and you encode them as operations and lift it to the weak world and all that. Well, that may or may not work, but today I'm giving you an example where it does work, which deals with this notion of weak equivalence between these algebraic weak common categories. So a weak equivalence is, well, a map between weak common categories. So this is strictly functorial. So what I mean by that is an algebra morphism between these algebras for this monarchy weak. And we want to talk about these omega functors that are essentially surjective on objects and fully faithful. Hopefully, you think this is a reasonable notion of weak equivalence. Well, but exactly what do I mean by these conditions? Well, essentially surjective on objects should mean that for any object in Y, there's an object in X that maps to that Y after suitable notion of equivalence. And that suitable notion of equivalence here is that of co-inductive one. So that is what I mean. Okay, that's the typo. That should be a little Y. But so this is what I mean by essentially surjective on objects. Now, what about fully faithful? Well, fully faithful should mean that the induced maps between the homes are, well, invertible in a suitable sense. But here we are taking homes of a weak omega category, and these homes are again weak omega categories. So saying that the induced maps between the homes should be invertible, that's saying that the induced maps between the homes are again weak equivalences. So this gives you a sort of co-inductive kind of definition, but if you unravel what that means, well, okay, so this is what I just said. But if you unravel that, this is saying that this induced map is, well, essentially surjective on objects in this sense, and then again, well, the induced maps between the next homes are weak equivalences. So you just keep doing that, and what you get is, well, okay, so a weak equivalence is an algebraic morphism that is essentially surjective on each level. So F itself is essentially surjective on objects, but also all the induced maps between the iterated homes are essentially surjective on objects. So that's what we take as the definition of weak equivalence. And here is the thing that we prove in our paper, which is that the class of these weak equivalences, in this sense, they have the 2 out of 3 property, which says that if you have a composable pair of algebra morphisms F and G, then if any 2 of F, G, and the composite GF, if any 2 of them are weak equivalences, then so is the third. So this is something that you'd hope to hold for a reasonable class of equivalences. So this is what we prove in your paper. And also, I said I will give you an example of a situation where you take the proof of the strict case and you encode everything as operations and then lead to a weak world, and that somehow works. So, so for this particular example, the proof of the strict case given by these 3 authors, so that was given as part of their construction of the fork model structure on the category of strict omega categories. So the proof of the strict case more or less generalizes the weak case smoothly. by, well, again, encode everything as operations and lift all the operations to the weak world, except for this lemma, which says that if you have a co-inductive equivalence little e, then whiskering with this little a defines a map between the homes, and we want this whiskering map to be essentially surjective on each level. So, you need this sort of lemma because, well, a weak equivalence is something that is essentially surjective on each level. So, like, you'll be carrying around these, like, weaknesses, the essential bits. So, these, like, you'll be carrying these co-inductive equivalences all the way, and at some point you have to deal with the fact that you have a co-inductive equivalence rather than an inequality. So, this is somehow like how you get rid of the thing that you have. So this is something you have to prove in order to show that these weak equivalences have the 2 out of 3 property. And in the strict case, this is somehow proven by reducing to the special case where this little a is the identity. Well, in the strict world, yes, I'm just going with the identity, like literally does nothing, so this is true. But in the weak world, well, this is non-trivial because the identity is not the strict identity. So, let me show you, at least at the, maybe not the lowest dimension, but the next dimension up, exactly what this statement is saying. Okay, so, what does it mean for the whiskering with the identity to be essentially surjective on one cell? Well, what we have is a one cell in the home, so this would be a 2 cell, which points from F composed with an extra identity to G composed with an extra identity. So this U is of this form. And then we want a 2 cell that points from just F to just G, such that if you whisker this with the identity, you get this original U back. So this is what the essential surjectivity on the one cells means. So what do we do? Okay, so we have this thing pointing from the identity F to the identity G. Well, but we have these witnesses to the unit law, so we can just compose with these things. So that is, I guess, a reasonable candidate for what this V is. So now this V actually points from just F to just G. So that's just the original cell sandwiched between these witnesses to the unit law. But, well, we have to show that if you whisker this V with an identity, then we get the original U. So here's a picture. So this was our V. And if you whisker that with the identity, do we get this U back? Well, so if there was, okay, so this, is true in the strict world. So, if, what I said on the previous slide was true, then probably you can just take, that relation from strict world, encode that as an operation, and lift it to the weak world. So we would want an operation that takes a U like this, and then outputs a 3 cell pointing from, let's say, here to here, which we don't actually have, because when I said we have all the operations, well, I was lying. There's actually a condition on somehow the arity of these operations, and here we, the boundary structure of the U, it's pointing from the identity composed of something to the identity composed of something. That's too complicated to fit in the arity that we actually have. If you remember the actual definition, basically we only have operations that you can specify as a cell in the free strict omega category. So, we don't have, something that points from a composite to a composite, which is not itself a composite in the strict, the free strict omega category, monocle to a set. So, anyway, we don't have a single operation that gives us a 3 cell like this, but we do have an operation that gives us something pointing from this. So this is the original thing with these more unit laws here and here, and also the same thing on the other side. We do have an operation that gives us a 3 cell like this. Why? Well, if we think of these shaded bits as just a composite here as a single thing, and same thing here. Well, on the right we have just this thing which points from F to G. And on the left, we have this unit law followed by the identity whiskered with this highlighted thing composed with this unit law again. So on this side is this. So this square, you can see as a sort of naturality of the unit law. I mean, it's not. I mean, here we have row check and row point in the other way. So I mean, maybe no. Well, I mean, you can see that this is a sort of naturality. So this is a relation that you have in the strict world. So now we can code this as an operation and then lift it to the weak world, and that's how we get this 3-cell, which is a co-inductive equivalence. And once we have this sort of thing, we can compose that with even more these unit laws. And then if we look at what's happening at the top and the bottom, then we have row comes to row check and row comes to row check, and the same thing on the other side. So we on the previous slide with lots of pictures, we had 3-cell connecting these composites to the identity, so we can compose with those and use more unit laws there and then get what we want. So this is the essential surjectivity on the 1 cells. And on the 2 cells, what do we do? Well, so we have now a thing pointing from U with respect with the identity to V with respect with the identity, and we have to first adjust the one-dimensional boundary, because now this is pointing from F identity to G identity, so we do unit law here and unit law here, but this still doesn't have the right 2-dimensional boundary, because the 2-dimensional boundary is that input with that, which is not equal to just U. So, and the same thing on the target side, so we have to do more of these things, and so on. So this is the limit of my drawing ability, so I stopped with pictures here, but anyway, in the general case, we prove it by basically systematically adjusting the boundary dimension by dimension, so you using unit law and higher unit laws to just construct the thing, the candidate for the thing that maps to your given thing after whispering with the identity. But then to actually show that that candidate works, you have to prove some sort of naturality of this adjusting boundary operation using lots and lots of operations. So actually lots and lots. I don't mean that. Anyway, so if you want to see all these details, here is the preprint on archive that went up just last week. Yay. And a few other selling points of our work is that, so if you know about how the strict case works, then they use cylinders. Instead of that, we focus on whiskerings, but somehow we avoid the use of general cylinders by instead of doing whiskering inductively, and that I think makes the proof a little more conceptual. You can sort of see what's going on. And also we extend our result to weak omega functors. So by this I mean we also consider maps that are only weakly functorial. Because if you want a nice notion of equivalence between these weak omega categories, maybe this is somehow more natural to consider. And the notion of weak omega functor we use is that of Richard sitting somewhere. Yes, hello Richard. Anyway, so that is, I guess, the end of my talk. So thank you very much.
Firstly, thanks for the great talk, Yuki. This is a very interesting project. I have a question regarding, you said that there were 2 different levels of these weak equivalences. One were things defined inside a weak omega category co-inductively, and then things which looked like maybe there were functors between right, so the question is whether you have a Yoneda embedding thing at this level, and whether these things can then be detected at the level of, natural isomorphisms between pre-sheaf, things, so that these notions can be reconciled, or if this is way further down the road, because I don't actually know.
Yes, it is way further down the road.
Yeah. Okay. Cool.
Yeah, we don't know how to construct weak omega categories. We don't really know how to express for example, the functionality of taking the home.
Okay.
Because because everything is weak. So, when I was careful with these slides, and what I mean by that is that here I said essentially subject on each level. I didn't say it's a weak equivalence because this is not strictly functorial. in the weak case. So that's another thing that you have to worry about on all this. Yeah. So what you're saying is like morally true, but we don't know how to prove that, or maybe not even how to state that. Yeah.
I have perhaps. Oh, sorry. Could I or?
Yes.
I have perhaps a question. Can you lift all the relations that you have in the strict case? Is there some method here that says that you also have it then as going back to the equivalence for the weak case?
So.
Do you believe that is true?
Yeah, so that is, I guess, closer to like, my talk at the previous city. So that, is that? I don't know. So at least you have something like, if you have like a bunch of cells that we can compose, then there are like many ways to compose that collection. And we have a theorem saying that if you like, as long as like what you do on the boundary agree, like whatever you do in the interior, you always get you have a unique composite after this conductor equivalence. I don't know, that might be
and
sort of.
Does this fit in there, or you cannot reach with that?
Sorry,
You cannot reach this new
sorry, I can't hear you.
You cannot reach this new tier with.
I mean, like we do use that result everywhere in proving this, but I mean, like the picture that I showed you today are sort of like the extra work that you have to do in addition to using that.
Okay, thanks.
So in the case of strict omega categories,
Yep.
having the 2 out of 3 property comes up in the construction of the folk model
Yep.
structure. Where do you see like the gap remaining to construct a model structure on weak omega categories?
The hardest bit is constructing the path object.
Yeah.
Well, I mean, I guess we're going to be talking about that at some point. But yes, but there's another thing about actually characterizing the vibrations by lifting properties, because I mean that's somehow there you need something like coherent equivalences, like a model for that, and like there was a recent preprint by some of the people here and other people, but like that, I don't think that quite works for like what we are doing. But we do have an idea on how to do that. So like that is not that difficult, I don't think. It's the path object, I think, is the impossible bit, it seems.
Yeah.
So two things which are possibly of the same order of magnitude as showing that we have a path object.
Yeah.
So, any progress in showing that those maps there are weak omega functors?
Yes, that is like on the same level. Like.
And then I guess another one, which is more obviously the same difficulty, is showing that every strict omega weak equivalence has a weak inverse, an inverse omega weak.
Yeah, that's somehow, like everything, like, yeah.
All the same thing.
Yeah.
Any questions? Yes.
You might have missed it. Did you say that the weak omega, the weak equivalences are weak omega groupoid?
Sorry, weak.
Did you say that if you have the weak, just the weak equivalences, does it form a weak omega category or a groupoid? I would expect a weak omega groupoid.
So you're talking about cells in a single weak omega category, or like things between?
Yes.
You don't
You said
know.
it says 3 for 2.
Sorry, it's.
You said it satisfies the 3 for 2 condition.
Oh, I see. Oh, there.
For a universe.
I see.
Weak omega.
Well, like we don't know how to construct an inverse to this sort of weak equivalence. So, I guess you don't want to call such a thing a groupoid.
Okay.
Okay, let's thank you again.
Thank you.